Okay, so we have come back to analysis. In this section, we are going to see about cardinality of sets. If you recall, we were going through set theory in the third chapter, to be specific, ZFC, and this is also the last section of the third chapter. In the second chapter, if you recall, we developed the system of natural numbers axiomatically. That means we assumed that there is a natural number called 0, and also every natural number has a successor which can be obtained by using this increment operation, and we assumed that this entire system is supposed to satisfy the 5 piano axioms. In this development, the natural numbers come out more like ordinals, and less like cardinals. There are entities in mathematics called ordinals and cardinals. We are not going to define them rigorously for two reasons. One of them is that it is beyond the scope of this text, and the other reason is that we won't need them. Roughly speaking, however, we can try to understand what cardinals and ordinals are, or rather, what is the difference between these two kinds of entities, and why are they related to natural numbers. Cardinals are these: 1, 2, 3, etc., and they are used to measure sizes of finite sets, or to count the number of elements in a finite set. As opposed to this, ordinals are these things. Etc. And they, instead of using them to count number of elements in a finite set, they are used to order objects in a sequence, and there is a subtle difference between these two usages. However, you can see that natural numbers themselves are used for both the purposes. They are used for putting an order into the objects of a sequence, or ordering the elements of a sequence, but at the same time they are also used to measure sizes of finite sets. Now this second use is how we conceptualize natural numbers when we are first taught about them in our schools. We learn about these numbers like 1 apple, 2 bananas, 3 oranges, something like that. But in our axiomatic development of the system, we have developed them as if they are ordinals. Now, these things in mathematics actually can be infinite. The finite part of these systems are like natural numbers. When we go to infinite cardinals and infinite ordinals, the difference becomes more pronounced. Okay, so now what we need to do is we need to address the issue that the way we conceptualize about natural numbers, or the way we think of them when we use them to measure sizes of finite sets, is that rigorous? Can that be done rigorously? And the answer, of course, is yes, and that's what we are going to do in this section. Okay, and that is one thing we have not addressed so far. We have done everything else with the system of natural numbers. We have defined the two binary operations of addition and multiplication, and we also have an order relation, and we have proved all the elementary properties that one can prove in this system. So those things are okay, but this part has been left out so far. So So we are now going to bridge this gap. Okay. So now let us ask, when do two sets have the same size? Before we can hope to use natural numbers to measure sizes of finite sets, we should be able to say when two sets have the same size. And keep one more thing in mind. We have not yet defined finiteness, or for that matter infiniteness of sets. That we are going to do here. Say for example, we consider these two sets. You would clearly say that they have the same size. It feels like they have the same size. But what is the reason? One may say that the sets have the same size because the number of elements in both of them is 3. However, this is something we have not yet defined, number of elements, or for that matter finiteness. So can it be done in a way that does not involve number of elements to begin with? That may be somewhat difficult to see at once, but with some thought that one can come up with this. Say, at a more elementary level, we can think of the situation like this. These two sets have the same size because the elements in them can be put into a one-to-one correspondence. Say like this: 0, 3, 1, 4, 2, 5. So that for every element in the first set there is a unique element in the second set, and also conversely for every element in the second set there is a unique element in the first set. Then we will say that these two sets have the same size, and this idea has two advantages. One of them is that this applies to sets which are infinite in the usual sense, what you already feel as in infinite set. For those sets also this idea applies. And the other advantage is that it does not use the natural numbers in its definition. So taking this as Q, we are going to define when two sets have the same size. Now, instead of saying size, we will say cardinality. So that's where the first definition comes, and it goes like this. So this is definition 361. Two sets X and Y are said to have the same cardinality or we say that X has the same cardinality as Y if there is a bijection f with x as its domain and y as its range. If this happens, then we will say that x and y have the same cardinality, or x has the same cardinality as y, same thing. Okay, and that's just the definition, and this should be thought of as x and y having the same size. Okay, now to illustrate this idea, let us look at the next example. Now in this example, the sets 0, 1, 2 and 3, 4, 5, the ones we have taken here, have the same cardinality, and in fact we have seen this, why that is so. This is a one-to-one correspondence or a bijection from this set into this set. Okay, now comes a point. Note that we do not yet know that the sets say 0, 1, 2 and, well, I can write any set, but let's just write what is given in the text. Don't have the same cardinality. In this case we know that the sets have the same cardinality because there is a bijection. However, we do not immediately know that these two sets don't have the same cardinality. For that, we have to show that there is no bijection. We may come up with a function, say if we define say a function f from 0, 1, 2 to 3, 4, 3, 4 like this. F of 0 say is 3, f of 1 is also 3 and f of 2 is say 4, then f is clearly not a bijection. This particular function is not a bijection, but that does not tell us that these two sets don't have the same cardinality. We have to show that no function can be a bijection. That can be a little difficult task because there may be many functions, and you can see that as there are more and more elements, as I'm tempted to say number of elements, but I can't say that. But you can understand what I am trying to say. If there are more elements in these two sets, The task of showing that they are not of the same cardinality just by going through all the possible functions and verifying that none of them is a bijection is a daunting task. It quickly becomes unmanageable, and so we need something else, some other way of saying that these two things, these two sets don't have the same cardinality. But there may be some other function from the first set to the second that is a bijection. Okay. So in this way, of course, it turns out that the sets don't have the same cardinality. And we will see this somewhat later. Show this. When we are equipped with better tools for showing that no bijection is possible, then we will conclude that they don't have the same cardinality. Note that one more thing. This definition means this one makes sense even when the sets involved are not finite. We don't yet know what finite means, so I am putting it within quotes. Although we haven't yet defined what finite means. Okay, so this is the situation. Now there is a remark after this. I think I need to refill. Give me a moment. the fact that two sets have the same cardinality. I hope you can see the same cardinality does not preclude the possibility that one of them may be a subset of the other. That is, if two sets have the same cardinality, or in loosely speaking the same size, then that does not preclude the possibility, that does not mean that one of them cannot be a subset of the other. It may be the case, and this is one of the reasons for opposing this idea to measure sizes of sets when they were first proposed, that in some situations, especially when sets become infinite, it happens that a set has the same cardinality with one of its subsets. So you can see, for example, if we already have a notation for this. If y denotes the set of all even natural numbers, then the function f from n to y given by f of n equal to 2n is a bijection, and the author asks why. So that means here you have to show that this function is a bijection. It's a function whose domain is the set of natural numbers and whose range is the set of all even natural numbers, and this is the definition of the function, rule for the function. So you show it's very easy why it's a bijection, and that is why, and hence x, okay, I am again and again writing x, n and y have the same cardinality, although y seems to have only half of the elements of n. That's how we feel, because if you look at the natural numbers in their natural ordering, you can see that these elements constitute y. So it feels like y has only half of the number of elements, we cannot say, but half of what x has, or what n has. Again I am saying x, excuse me. So because of that, y intuitively speaking should have been smaller than x. However, according to our definition, they turn out to have the same cardinality. So it may happen, and it happens only in case of infinite sets. We will see that later, why it happens only for infinite sets. Okay, so after this initial example and remarks, we now come to the first result of this section. This will be 364. Let x, y and z be sets x has the same cardinality as x. Okay. If x has the same cardinality as y, then y has the same cardinality as x. You can probably guess where it is going. We are actually being this proposition is asserting that having the same cardinality is an equivalence relation on the class of sets. If x has the same cardinality, the first assertion says that the relation is reflexive, the second one says it is symmetric, and the third one will say it is transitive. And y has the same cardinality as z, then x has the same cardinality as z. And its proof actually is an exercise. It's the first exercise. So when we solve the exercises, there we will prove it. It's really very easy, nothing difficult at all. And in fact, you don't have to do anything much. Whatever we need for proving this have already been proved for us when we proved many properties of bijections, properties of one-to-one correspondences. So in place of proof, we will just simply write this. See exercise 361. Okay. Now we come to the question of when we say that or the issue of associating actual natural numbers to sets and calling those natural numbers as the cardinalities of the sets. So let n be a natural number. We want to say that a set, say X, has n elements, or in other words, we want to say that that the number of elements in a set X is n. But how can we define that? Clearly, this set of all natural numbers that are greater than or equal to 1 and less than or equal to n, according to our definition, whatever it is or whatever it turns out to be, in the end, we require this set to have n elements. Our definition should match with our expectation. We expect this to have n elements, and our definition should give us that. Okay. And there is one more thing that we should note, that this seems true, or instead of writing it like this, note that this also, what should I write? Holds when n is 0, because for us natural numbers can be 0 also. That is the first natural number that we came across. In that case, the set that is when n is 0, this is empty, this is the empty set, which according to what we feel about number of elements in a set, the empty set should have 0 elements, or its cardinality should be 0. Okay, so we take this as the basis of our definition, and we are going to define using this and the notion of having the same cardinality we define this. This will be definition 365. Let X be a set and n be a natural number. We say that X has cardinality n. We say that X has cardinality n if it has the same cardinality as this set. So we will say that X has cardinality n, or the number of elements in X is n, when X has the same cardinality as this. And what is the definition of having the same cardinality? It means that there is a bijection between X and this set. If that happens to be true, then we